So we want to look at just a little bit more again with exponential decay. So meaning it's decreasing. We've done it with a table, so let's look at that. We would find that factor that we're multiplying by. And to do that, I would always take my bottom number divided by the number just above it. And when I put that into the calculator, 50 divided by 62.5, I get 0.8. It shouldn't matter where I do that as long as I take the second number divided by the first number. And I get 0.8. And I can also take that first number times 0.8 and then continually multiply by 0.8. And as long as you type in the number first times 0.8, you can just keep hitting enter, and I can see that it matches my table. So our initial value happens at 0, so 62.5. If we didn't remember, we could multiply back to get that next number. Our decay factor is 0.8. A decay factor has to be between 0 and 1. It can't be negative, because when you're multiplying by it, it would go negative, positive, negative, positive. That's not what we're looking for here. The decay rate is a little bit different. So decay rate, remember, is a percent that's leaving. And so we did this with a growth rate before. So this one, it isn't 80%. What we're going to do is we're going to do 1 minus 0.8, and then we're going to multiply it by 100, because that will get us into a percent. And we end up with 0.2 times 100, or 20%. So the decay factor is what is left, and then the percent is what's leaving. So equation y equals 62.5, that's what we're starting with, 0.8 to the power of x. There's another one, I'm going to have you try that one on your own. We're going to do some decay factors to decay rate. So convert a factor into a percent. So it's kind of just slightly different than I did up above. It just is putting it into a percent first as opposed to I put it into a percent last. Subtract that percent from 100, and this is your decay rate. So up above, we would have had 0.8 times 100 to get 80%, and then we would do 100 minus 80 to get 20%. So slightly different steps. It still works. If I give you a decay rate, so remember this is going to be a percent, the first thing we're going to do is put it into a decimal, and you're going to subtract this rate from 1 or 1.0, and this value is your decay factor. So we're going to practice that. We already did 0.8. We know that that's going to be 20%. If I know 6%, that's going to be the directions up in here. That's already given it to my, as a rate. I'm going to put it as a fraction or as a decimal. To do that, remember we're just dividing by 100 because percent means out of 100. So 6 divided by 100, I probably can write it in here, equals 0.06. And then we need to do 1 minus 0.06, which is 0.94. So my decay factor is 0.94. And this decay factor is really what is left, or what remains. And the decay rate is like how much is leaving. So that's one way to think of it. So 0.95 would be 95%. Multiplying it by 100 moves the decimal over 2. And then we're going to do 100 minus 95, which would give me 5%. 0.6 is 60%, so I'm going to do 100 minus 60%, which will give me 40%, which going the other direction again, but we could put it as a decimal, and 1 minus 0.4 would give me 0.6. So being able to go between those two is going to be helpful. I just want to go through the problem that we have here, at least a couple of them, and then you can still check the rest of them on your own. Chen cuts a sheet of paper in half. He stacks 2 pieces and cuts them in half. Then he stacks the resulting 4 pieces and cuts them in half, and so on. So we've got things started on here. We've got the number of cuts and the area. So 1 cut tells me that we have an area of 1 piece would be 32. We cut it again. We have an area of 16. So when we have the table, we can actually do this 32 divided by 64. To be able to figure out what's going on, and that's going to give us a factor, and since it's going down, it will be a decay factor. So this is 0.5. So it's going to be cut in half An equation is going to be my starting amount, 64, times 0.5 to the power of x. And we can fill these in here. Dividing by 2 makes things nice and easy. 2.5 and then 0.125. On our graph, number of cuts is going to be on our x-axis. And I'm just going to go up by 1, starting with 0. And our area, we need to go up to 64. So I'm going to go up by 5s. I'm going to call it area of ballots. And if you need to pause, go ahead and pause as you're catching up here. And then we're just going to graph our points on there. So at 0, it's at 64. Estimate the best we can. 1 would be at 32. 2 is at 16. I'm at 4, 4. 5, 2. And it's just really getting super tiny down here. It's almost hard to see those. Technically, we shouldn't connect the dots. I'm just going to connect them with a highlighter, I think, because that way you can still see it. You can see our dots. That's more important. But I want you just to kind of see the shape of the graph. But we wouldn't connect it because we don't really have a half cut. That's not something we can truly have. But I want you to be able to see that downward curve a little bit. So the pattern is going to be different from the fact that it's going down. And remember, it's not a slope. So the curve goes down. And it just starts really high and it drops pretty fast. And it's similar, because our upward curve, it's just going to kind of go up slow and then go up really fast. So it's almost like they're just a reflection of each other. So it's, I'm going to say sort of a reflection. Just because of how they would go. If this would be a doubling graph, that would look almost identical as long as our other numbers all lined up. They all have a curve, so we're going to add that. I should say both have a curve. If you don't see the curve, you're just not graphing enough points. From linear patterns, so from linear, oops, I don't have to write linear. I needed to write different. Linear has no curve. Whereas, that makes me sound smart, I feel. Exponential curves. Linear also goes like by the same amount every single time, and exponential would go by different amounts. I just don't have enough room to write that. And the same, similar part, something that's similar is that linear is going to add the same amount. And add also would be subtract, because it would just be adding a negative, since I don't have room to go back in and do add slash subtract each time. And exponential multiplies, and we don't refer to that one as a divide, because you just multiply by a fraction. Multiplies by the same amount. And then I'm not, oh, I was going to say I wasn't so sure if I wanted to. This one, I think you're going to do most of it on your own. I just want to explain it a little bit. We have a graph of the state of the data. And then we also have a chart of the data, so you can get the exact numbers here, as opposed to having to look at those and kind of guess what's going on. And this is just finding that, in this case, a decay factor. So how we find the factors, as we have for a long time, writing an equation, and then look for what are the things that are the same. So look for kind of like broad concepts that are the same. Obviously, our numbers are going to be exactly the same, but does the shape of the graph look the same? Does our tables look similar? What kinds of things can you look at that can say that's pretty much going to be true? And then obviously our numbers would be different, would be one thing we can talk about. All these answers will be on the Canvas page, so you're free to check them from there.